Section 12 of The Outline of Science, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Michelle. The Outline of Science by J. Arthur Thomson. Chapter 21. The Romance of Chemistry. Part 1. When we first visit a great museum, we are impressed by the multitude of different kinds of things. These thousands of startlingly different species of animals, each itself and no other, these hundreds of different kinds of wood, shelf after shelf of minerals, and Aladdin's cave of precious stones, besides all manner of things artificially made, such as alloys and fabrics, drugs and preserved foods. Some of the objects we see may fade into one another, but what almost embarrasses us is the number of things that are quite distinctive. We get the same impression of diversity when we take a walk in the country, or when we see a dredge or a trawl brought up on deck, shuffling the chemical cards. Now a kindly curator in the museum might take us to the bird cases, for instance, and show that, after all, the diversity was in great part due to different shufflings of a not very large pack of cards. There are thousands of tunes, but there are not many notes. He might take us to the case of minerals, where by ourselves we got the impression of overwhelming and baffling variety, and show us that a comparatively small number of really different things may be shuffled into a multitude of diversities. A small cast of players may form a great variety of different tableaux. There might be in the museum a case showing a sheet of parchment paper, a slab cut out of a tree, a wooden pot full of glue, a cork for the same, a piece of India rubber for erasures, a celluloid beaker full of water, a lead pencil, a vulcanite holder, a pad of blotting paper, a lump of sugar, a little starch, and 100 other things, as different could be, including even a diamond. And yet the label of the case might correctly state that all this variety included only 3 elements: carbon, hydrogen, and oxygen. Perhaps this is one of the big revelations of chemistry for ordinary people, that in spite of the immense variety of things in the world, there is only a relatively small number of things that are really different, namely, the 80 or so chemical elements. We do not know how many words there are in the English language, but there are only about 26 generally recognized letters. It is the same in chemistry: many different hands, but not such a large number of cards. Furthermore, just as there are some letters like Q and Z which are not in very frequent use, in the same way it must be noted that many of the 80 or so chemical elements are rare, and do not occur in more than a small percentage of the specimens in the museum. Many of the rare earths, though very important for man's purposes, do not play a large part either in the architecture or in the bustle of the world. They lurk quietly in remote corners. Take tantalum, for instance. It has been calculated that there are, on a very moderate estimate, 250,000 of very different kinds of things in this world of ours. But scientific chemistry has shown that this multitude is due to varied groupings of about 80 really different kinds of stuff, namely the chemical elements. It is not easy to put the case rightly, for each fresh pattern may be something very definitely new and individual, just as a painter makes many pictures of the same few colors. Everyone knows the variety of patterns that result when the pieces of colored glass in a kaleidoscope are shaken into new combinations, but this is a static diversity. It suggests, however, what may result from the shuffling of a few elements, especially when some of these are what is sometimes called attractive. In general terms, the conclusion to which common experience and exact science lead us is this: that given a small number of sociable elements, there may be many a ménage. From a few elements, even from fewer than we can count on the fingers of our 2 hands, there may be a new world. And the view is widely held among chemists that there has arisen from one elemental stuff the whole array of known elements. Section 1. In a previous chapter, The Foundations of the Universe, the problems which the physicists and the chemists of to day are so eagerly investigating were fully discussed. We saw there how it has come about that all the observed phenomena of chemistry and physics are regarded as indications of the fundamental unity of matter. All matter, in short, is supposed to be, in its final analysis, essentially the same in constitution. The atoms of all matter consist of particles of positive and negative electricity. The simplest atom, that of hydrogen, is a unit of negative electricity, called an electron, revolving around a nucleus of positive electricity, called a proton. Electrons obtained from different atoms are found to be the same. In an atom of hydrogen there is one electron, in an atom of helium two, in an atom of lithium three. The addition of further electrons to the system gives rise to the atoms of all other elements. All matter is thus supposed to be electrical in its nature. The atom, since its disintegration is seen to take place, is no longer the atom indivisible or incapable of being broken up into something simpler. It is not now believed that each of the 80 or so elements known to us has its own kind of atom, each stamped with its own properties. The properties and qualities of the different elements, it is believed, depend on the number and arrangement of the particles of negative electricity (electrons) and of positive particles (protons) contained in the atoms of the various elements. The view is that all the elements, though they have different chemical qualities, are built up out of the same material. Thus our ideas regarding the constitution of matter and the framework of the universe have been completely changed. The superlatively grand question is, what is the inner mechanism of the atom? It is the business of the chemist to attempt to fathom the mysteries of the properties of the various chemical elements, to evolve order and system out of them. It is to the chemist that we owe our knowledge that the atoms of different substances can be arranged in a definite order, and also that they show an increasing complexity of structure. Heavier atoms appear to behave as though they were evolved from the lighter. Forms of matter. It is well known that under suitable conditions the same type of matter can exist in three distinct forms: solid, liquid, and gas. In passing from one state to another, it is a matter of common knowledge that there are remarkable changes in appearance and physical qualities of an element. These changes are believed to be connected with the average distance which separates one atom or molecule from the other, and in the rapidity of motion. In the gas or vapour form, the molecules are on an average so far apart that their mutual attractions are relatively unimportant. The lowering of the temperature, the distance and rapidity of motion of the molecules diminish until, under certain conditions, the attraction of the molecules for one another predominates, resulting in a much closer packing in the appearance of the liquid form. The molecules, however, still retain a certain freedom of motion, but this is diminished with the lowering of the temperature, until at a certain stage the molecules form a tighter grouping, corresponding to the solid state, where the freedom of motion of the individual molecules is much restricted. In order to account for the resistance of solids to compression or extension, it has been supposed that the force between molecules is attractive at large distances, but repulsive at small distances. While we are able to offer a general explanation of the passage of an element from one state to another, a complete explanation of such phenomena will only be possible when we know the detailed structure of the atoms and the nature and magnitude of the forces between them. It is well known to everybody that the atom of one chemical element may combine with one or more atoms of another element. When the chemist speaks of the valency of an element, he means the number of other atoms with which one atom of this element can directly combine. For example, one atom of hydrogen combines with one atom of chlorine, and the result is hydrochloric acid; or one atom of oxygen will combine with two atoms of hydrogen, and the result is water. One atom of nitrogen combines with three of hydrogen, and we get ammonia. Each of these combinations represents a chemical process, that is to say, a chemical change which produces a substance which is totally distinct, not a substance which merely partakes of the characters of the two component elements. Thus are the various substances built up. The elements are mostly found in mutual combinations, and the combinations are sometimes of course very complex. While a particle or molecule of water consists of two atoms of hydrogen and one of oxygen, The molecule of the proteid, called albumin, is built up by 72 atoms of carbon, 112 atoms of hydrogen, 18 atoms of nitrogen, all brought into association with one atom of sulphur. In all protoplasm of living matter there is a mixture of proteins, carbohydrates, and fats, with intricate chemical and physical interrelations. It is highly improbable that there is any one substance which deserves to be called the living matter or protoplasm. What we actually know is a complex and heterogeneous system in which various chemical reactions take place simultaneously. There is always involved, as life goes on, a breaking down and a building up of proteins. But the riddle is still unread. Some biologists hold the view that there is an ultimate molecule of life hidden in the protoplasm, which holds the secret of the endless building up and breaking down. Sir Ray Lankester gives this supreme life stuff the name plastogen, and he says in regard to its workings that whilst they can be grouped with the chemical and physical qualities of other bodies, they so far transcend them in complexity and in immensity of result, the whole creation of plant and animal life, that their appearance constitutes in effect a new departure, a sudden and to us unaccountable acquirement. But then we must remember that it is also an unaccountable thing to us that water suddenly becomes ice at a low temperature, and suddenly becomes vapour at a high temperature, even if we are able to imagine the mechanism which necessitates these changes. We cannot explain the nature of things, even though we can classify them and arrange them in order, and more or less satisfactorily guess what their inner mechanism is. We cannot, in our present state of knowledge, trace them in detail to a first beginning. 2. Some of the elements in their natural conditions are gaseous, like oxygen, hydrogen, nitrogen, chlorine, etc. Mercury and bromine are liquids, while a great number, chiefly metals, are solids, like gold, iron, zinc, etc. Professor Meldola says with respect to the distribution of the elements: "It is of interest to note that more than three-fourths of the accessible crust of this globe upon which we live is made up of two non-metals, oxygen and silicon, about one half being oxygen. Nothing affords more striking evidence of the marvel of chemical change than the contemplation of this geo-chemical fact, that the superficial solidity of the earth is due to the predominance of those mineral constituents into the composition of which gaseous oxygen and the non-metal silicon enter to a preponderating extent. The whole crust of the earth with which geology deals is composed to the extent of more than 99% of only about 20 out of 82 elements." This will give an idea of the rarity of some of the materials which the chemist has had to deal with. Mixtures and compounds. There is an obvious but important difference between a mixture, like sand plus sugar, like iron dust plus chalk, and a compound, like sugar or like chalk. A mixture is never homogeneous. It can be divided into different ingredients. A compound is always homogeneous. Its particles, however fine, are all the same until we begin to break up the compound into its components. With water we can dissolve away the sugar from the sand. With a magnet we can pick away the iron particles from the chalk. But it is usually necessary to take more thorough-going measures to split up a compound. It must not be supposed, however, that the distinction between a mixture and a compound is always easy. Air looks very homogeneous, but it is a mixture of a great crowd of oxygen particles, a still greater crowd of nitrogen particles, and small crowds of carbon dioxide and water vapour particles. Nothing seems more homogeneous than water, but pure water is never found in nature. There are always impurities in it, and one needs only to bring a glass of cold water into a warmish room to see how multitudinous bubbles of gas form on the inner walls of the vessel. These suggest, at any rate, that there is a good deal of gas mixed up with water. If this were not the case, no animals could breathe under water. For while water is a compound H2O of hydrogen and oxygen, it is not possible for animals to separate the two components the way plants are able to do with the carbon dioxide CO2 mixed in the air or the water. Perfectly pure substances, though often advertised, are very difficult to obtain. They are indeed almost ideal, which led a great investigator to say that Chemistry is the science of substances which do not exist. Traces of impurity in a substance are often of great practical importance. They sometimes influence the properties of the substance in a remarkable way. We quote a sentence from Dr. Mellor's admirable text book, Modern Inorganic Chemistry (1920). H. Vivian says that 1,000th part of antimony will convert the best selected copper into the worst conceivable. Lord Kelvin says that the presence of 1,000th part of bismuth in copper would reduce its electrical conductivity so as to be fatal to the success of the submarine cable. And W. R. Roberts Austin says that 1/500th part of bismuth in gold would render gold useless from the point of view of coinage, because the metal would crumble under the pressure in the die. Molecules and atoms. A mixture can usually be separated into its ingredients by more or less simple mechanical means. A compound cannot be broken up into its components without going beyond simple mechanical methods. We break a piece of salt into finer and finer powder, but each particle of salt dust remains salt. If we could get hold of a particle which would cease to be salt when we broke it in pieces, that particle would be a molecule of salt, and we should have divided it into groups of constituent atoms, sodium atoms and chlorine atoms. A lump of salt is built up of a prodigious number of molecules of salt, and each molecule is a little building of which the atoms are the bricks. To return to the elements. An element has been defined as a substance whose molecule contains only one kind of atom. But this definition must be modified in relation to the fact that the elements uranium and thorium give rise, as we shall see, to other elements different from themselves. Nevertheless, the general idea remains that an element is a unique and homogeneous kind of matter. When an electric current is passed through water, H2O, it decomposes it into hydrogen and oxygen. Bubbles of oxygen may be collected at one pole and bubbles of hydrogen at the other pole. This is a fact. There is a theory, perhaps more than a theory, that free atoms of oxygen travel in one direction and free atoms of hydrogen in the opposite direction through the water. Ion, the Greek word for a traveller, is the term applied to these particles which travel to the two electrodes during electrolysis. Ions are travelling atoms or groups of atoms which are started on their journey by the dissociation of the electrolyte, say water, and they are believed to carry opposite charges of electricity. Each molecule that is split up gives rise to two kinds of ions: anions going to the anode pole and cations going to the cathode pole. And these two kinds of ions are furnished with equal and opposite charges. The ion with a positive charge of electricity is attracted to the cathode, or negatively charged electrode, and the ion with the negative charge is attracted to the anode, or positively charged electrode. And each ion will then be relieved of its charge and become an ordinary atom again. The speeds of the migrating ions have been measured, and it seems that the heaviest ions, for example, with the greatest atomic weights, move fastest. It has been supposed that this is due to the more slow-going ions dragging along with them a number of molecules of the solvent. This is very theoretical, but everyone knows the practical application in silver plating and the like. A brass spoon, let us say, is immersed by a wire in a solution of silver salt, say a solution of silver cyanide in potassium cyanide, and the spoon is the one pole, the cathode. A sheet of silver is the other pole, the anode. A weak electric current is passed through the fluid, and cations of silver are then deposited on the brass spoon, which becomes a silver plated spoon. Mr. C. T. Kingset, in his Popular Chemical Dictionary, says of chemical changes: "All articles of food and clothing, the materials of which our houses and buildings are constructed, and which are needed for their decoration or repair, every art and every industry, all depend essentially for their production or activity upon chemical changes, as realized in nature or made by man to serve human purposes. The same is true of the production and decay of animal and vegetable matters, as also the process by which they are broken up and the resulting products made available in their turn as food for new life. These chemical changes constitute a sort of adaptation of matter to environment, and in a sense are acts of creation, as every such change produces products which, although related, are quite distinct in character and in properties from the original substances which give rise to them when subjected to the required influences. Thus, in a very literal sense, all matter, which, as will be seen in other places, appears to be essentially one in nature, is actuated by a spirit of life, being susceptible to change when the environment is appropriate. Chemical change. Chemistry is concerned with the different kinds of matter in the world and with the changes which they produce by interaction. If a bar of iron is heated it becomes longer, but it returns to its original length when cooled. We call this a physical change, for the iron remained iron from first to last. But when a piece of iron left out of doors begins to rust, we call this a chemical change, for the iron becomes something different, namely, iron oxide, with quite different properties. This iron rust is not transmuted iron, but iron in combination with oxygen, and that is a very different thing. Chemical changes always imply a shuffling of the cards, a new arrangement of partners. Pie man plus pie, as the American expositor puts it, on the one side, boy plus penny on the other side. A change occurs, and the situation is pie man plus penny, and boy plus pie. This sort of thing is going on ceaselessly all the world over. It is necessary to say, however, that the boundary line between chemistry and physics has become very indefinite, especially in light of the fact that the qualitatively chemical differences between uranium and radium, or thorium and radium, seem to depend on quantitatively physical differences in the corpuscles of electricity. Demonstrating the invisible. Many of the materials with which the chemist deals are invisible, and so is the air we breathe, as long as it is dry and clean. In ordinary circumstances none of us ever sees oxygen, hydrogen, nitrogen, or carbon dioxide, and yet all of these are as real as iron and lead, sulphur and diamonds. As Professor James C. Phillips says, "A gas may be without smell or taste, it may be as intangible as a spirit, and as for seeing it, why, it may be off and away while the observer still thinks he is looking at it." Now, it is worth while pausing to ask how the chemist is so sure about what he cannot see, why he must reject the proverb, "Seeing is believing." Invisible materials betray themselves by what they do. The oxygen rusts the iron. The carbon dioxide which we breathe out into a beaker of lime water makes the water cloudy. A mouse lowered into a shaft containing the deadly carbon monoxide gas is killed. The danger of this poisonous gas escaping from a leaking or badly burning stove is well known. White mice used to be carried by submarines in order to detect the dangerous CO gas. But there are finer methods now in use. When a tumbler is inverted into a basin of water we cannot press it quite down, and we know that the rise of the water is being resisted by the invisible air in the tumbler. Sometimes we can ourselves almost lean up against the rapidly moving invisible air. Still more convincing is the test by which Lavoisier founded modern chemistry, the test of the balance. For every invisible material has its weight, even the hydrogen, which is 14½ times lighter than air, and therefore lifts the balloon so easily. We do not need to go any further in indicating how chemistry demonstrates the invisible, but it would be dull indeed not to refer to the modern demonstration of invisible gases by turning them into liquids or solids. Section 3. Liquefaction of gases. Modern science has given us a vivid picture of that condition of matter which we call gaseous. Professor Clerk Maxwell compared the molecules in calm air to a swarm of bees, when every individual bee is flying furiously, first in one direction and then in another, while the swarm as a whole either remains at rest or sails slowly through the air. But we have to add to the picture the collision of one bee with another bee, for a molecule can travel only a short distance, its mean path, without striking another. Indeed, as Clerk Maxwell calculated, the number of collisions which a molecule must undergo in a second must be reckoned by thousands of millions. In his famous discourse on molecules he spoke of the time it took for the smell of an opened bottle of ammonia to pervade the room. The molecules of the ammonia have a velocity of 600 meters per second, but they are not able to spread at that rate through the room. They strike against the molecules of air and are delayed. Each molecule of ammonia is so jostled about by the molecules of air that it is sometimes going one way and sometimes another, and like a hare which is always doubling, though it goes at a great pace, it makes very little progress. Gradually, however, the ammonia gas does spread through the air of the room. In a liquid, as contrasted with a gas, the molecule has hardly any free path, but is always in a state of close encounter with the other molecules. In a solid, the molecules have almost lost their opportunities for moving about. Now everyone knows that water vapour may condense into flowing water, and that this may freeze into solid ice, which may melt again and steal off as a mist. Saturated steam above 720.6 degrees centigrade is a gas. Thus water occurs in four states. The passage from phase to phase is familiar, but in the liquefaction of gases it became dramatic. About the beginning of the 19th century, Northmore and others liquefied sulphurous acid gas by pressure, but progressive research on the liquefaction of gases began with the work of Faraday and Sir Humphry Davy in 1823, when chlorine, carbonic acid, ammonia, and other gases were liquefied by great pressure. Later on, Thélaurier showed how the evaporation of a jet of liquid carbonic acid produces cold so great that the rest of the jet is frozen into fine snow. There is a temperature above which no amount of pressure will produce liquefaction, and it was not until devices for securing very low temperatures were discovered, and this was a great achievement of modern science, that it became possible to liquefy oxygen, nitrogen, and the like. But with the invention of methods of obtaining very low temperature, which brings the molecules close together, just as heat drives them apart, oxygen and nitrogen were conquered, and in 1898 Professor (now Sir James) Dewar produced liquid hydrogen. As Professor Tilden remarks, "It was both interesting and gratifying that the final victory, which crowned the long series of successful attacks upon the apparently impregnable position of the permanent gases, should have been recorded in the laboratory of the Royal Institution, where the first successes in this field were won by Faraday." End of Section 12. of The Outline of Science, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Michelle. The Outline of Science, Volume 3, by J. Arthur Thomson. Chapter 21. The Romance of Chemistry, Part 2. Transmutation of Elements. The chemists or alchemists of the Middle Ages sought after the philosopher's stone, which would transmute base metal such as lead into gold. Some even believed that their quest was successful, for the science of chemistry was not far enough advanced to dispel their illusions. If a knife blade be placed in a solution of blue vitriol or sulphate of copper, it comes out like copper, and, as Professor James C. Phillip points out, to the alchemist the result admitted of no other explanation than that the iron had been converted into copper. We know now that no such change takes place. Some copper comes out of the solution and is deposited on the surface of the iron, while by way of holding the balance even, an equivalent amount of the iron passes into solution. The transmutation of one element into another was discredited when the science of chemistry began to get on its feet, and just as naturalists believed in the fixity of species, so chemists believed in the immutability of the elements. Each element is itself and no other. But everyone knows the change of view that the discoveries of the 20th century have brought. It is now established that the element uranium may in part change into radium and some other elements. A spontaneous change occurs, associated with the partial disintegration of the uranium atom, which leads to the formation of minute quantities of radium, apparently with ionium as an intervening link. From another changeful radio element, namely thorium, there may also be derived at a very low rate minute quantities of radium. It appears that the uranium and thorium give off particles of helium, an element first detected in the sun and restricted, as far as the earth is concerned, to minerals containing the two radio elements just mentioned. The final product of the metamorphosis appears to be lead, and in this way a radioactive mineral may be utilized as a geological clock. Professor Cites explains this. In a uranium mineral, each 1% of lead in terms of the quantity of uranium signifies a lapse of a period of 80 million years. Errors, of course, are possible.
If lead should have been an original constituent of the mineral, but these are minimized by taking a large number of different minerals. On the other hand, every cubic centimeter by volume of helium per gram of uranium in a uranium mineral signifies 9,000,000 years, and as here helium, being a gas that forms no compounds, cannot have been initially present, and as moreover some will have escaped, the age of the mineral by this method is a minimum, whereas the age by the lead content may be too high. The carboniferous rocks tested by this new method appear to have an age of some 350,000,000, and the oldest Archean rocks of over 1,500,000,000 years. The difficult subject of radioactivity has been referred to in other chapters, but it cannot be more than touched on in a work of this scope. Enough has been said, however, to show that the doctrine of the unchangeableness of the chemical elements requires revision. We have already quoted from Professor Soddy, well known as one of the brilliant pioneers of the study of radioactivity, and we select a summing up sentence. The radio elements are in course of spontaneous mutation into other elements, and the process proceeds through a long succession of more or less unstable intermediate elements until the final stable is reached. In the domain of things, this is the nearest analog to evolution in the realm of organisms. Section 4. Chemistry of the living creature. Of the 80 and more elements, no fewer than 29 are known to occur in living creatures, but 12 of these are rare. Those that are always present are hydrogen, carbon, oxygen, nitrogen, phosphorus, sulfur, potassium, magnesium, calcium, and iron, and to these there should probably be added sodium, chlorine, and silicon. Not uncommon are iodine, for example, in brown seaweeds and the thyroid gland; manganese, a trace in most animals and in some plants; bromine, in brown seaweeds, a trace in some animals; and fluorine, in bones in a few plants. The first big fact is that the elements invariably present in organisms are common in the inorganic world. The second big fact is that the essential and most important elements in living creatures are hydrogen, carbon, oxygen, and nitrogen. In most animal and plant proteins, sulfur is also present in addition to the big four. In nucleoproteins, like the chromatin of the nuclei of all cells, there is likewise phosphorus. As far as the constituent elements go, there is nothing peculiar in living matter. On or near the surface of the cooling earth there would be a natural abundance, the chemists tell us, of water and CO2, and in this triumvirate there is a unique ensemble of fitness for forming the stones and mortar of the house of life, unique, for instance, in the synthetic possibilities of carbon, in the solvent power of water, in the stimulating power of oxygen set free by the dislocation of CO2, and in the attractive capacity of all three, drawing in other elements, such as magnesium and iron, to serve fresh purposes. It may be of interest to notice individually some of the common elements that occur in living creatures. Hydrogen ions are very important in respiration and gastric digestion. Oxygen is a releaser of energy in vital combustion and an attractive agent bringing in other useful elements. Water, H2O, is a chief constituent, over 70%, of living matter. Nitrogen combines with carbon, hydrogen, oxygen, and a little sulfur to form proteins, and all living implies the building up and breaking down of proteins. It gives living matter its restless explosiveness, because it is loath to combine with and easy to dissociate from most other elements. Carbon is unique in its capacity for forming compounds, of which more than 100,000 are known, and its combination with oxygen, CO2, affords the source from which most of the free oxygen of the air is derived. The remarkable power of carbon. The chemistry of carbon is of a peculiarly interesting nature. Because of its remarkable power of uniting with itself as well as with other elements, it is enabled to build up single molecules containing very large numbers of atoms, and such molecules form the basis for framing the structure of living organisms. Without these two properties of the carbon atom, life, at least as is known upon the earth, would be impossible. It is this element, in combination with a few other elements, for instance, hydrogen, oxygen, and nitrogen, which gives rise to a multitude of compounds of every degree of complexity, and out of which many substances are produced which are essential in building up the bodies of animals and plants. As we have seen, living products are chiefly based on four elements: carbon, nitrogen, oxygen, hydrogen. From these four elements, with admixtures, most substances of the living world are made up. It is a curious fact that all life on the earth should depend on two single factors: one, the presence of a mere trace lying at the level of only between 3 and 4 parts per 10,000 of this gas, carbon dioxide, in the air; and two, the natural power of the carbon atom contained in the carbon dioxide of entering into energy relationships with fellow carbon atoms. Given these conditions, a suitable form of energy and a suitable transformer for that energy, capable of turning it into chemical energy of carbon compounds, and it follows that all the complex constituents which form the basis of life not only can but must arise. As we have seen in a previous chapter, the energy transformer is the green plant cell aided by the green coloring matter called chlorophyll which it contains. It is interesting to note that carbon exists on Earth in different forms. There are 3 modifications of it to be found, all very different in outward appearance, and it may be added of different values in human estimation. We have carbon in the black and opaque form of charcoal, and as graphite or common blacklead, and in the transparent crystalline form of a brilliant diamond. All of these are merely different forms of the same stuff, and yet, although successful efforts have been made to manufacture artificial diamonds, it has not been found possible to do so on a commercial basis. That is to say, it is still cheaper to procure them by expensive means from the natural resources than to manufacture them in the laboratory.
The regulation of vital phenomena. Sulphur in small quantity is an essential part of the CHONS compounds called proteins. Phosphorus is necessary for the formation of chromatin, which is so important as a vehicle of hereditary characters. It is essential in the formation of tissues so different as bone and brain. Potassium is the most active of metals biologically considered, and its salts play an important part in the regulation of vital phenomena. Magnesium is an essential constituent of chlorophyll, in the making of which iron is also necessary though not included in its composition. Iron also occurs in the red pigment of the blood which captures oxygen from the outer world. Calcium compounds play an important part in stimulating or slowing vital processes. So we might continue, but we have said enough to suggest the manifold ways in which the various qualities of elements are utilized in the service of life. Section 5. Circulation of matter. One of the epoch-making ideas in science is that of the circulation of matter, a corollary of the idea of conservation. It is an old idea, for one of the Greek philosophers, Heraclitus, is responsible for the epigram, "All things flow," but its demonstration belongs to the 19th century. Just as we associate the name of William Harvey with the circulation of the blood, so we should link the name of Justus Liebig (1803 1873) with vivifying the fact of the circulation of matter. Many people know the name of this great chemist in connection with beef tea, but he has greater claims for commemoration. Everyone knows how the clouds condense on the cold rocks of the mountains, how the drops of water flow together into runlets, how they fill up the bog moss sponges and overflow into streamlets, how these make rivers which join the sea, how the sun-drawn mist rises from the ocean and forms the clouds which break on the mountainside. So the world goes round. But this is far too simple a case, for we have been dealing with water from beginning to end. Let us take a better case. Circulation of nitrogen. All living matter includes the nitrogenous carbon compounds called proteins, such as white of egg and the gluten of bread. In other words, all living creatures require nitrogenous supplies. Animals obtain these by eating other animals, or by eating plants, so we may leave them for the moment out of account as far as the problem of nitrogen supply is concerned. The question is where plants obtain nitrogen, and the generally valid answer is that the roots absorb nitrates and the like from the soil. There is abundance of nitrogen in the air. Indeed, 4/5 of the atmosphere is nitrogen. But this treasure house is closed to plants, except in the case of sundry types which, with the help of partner bacteria (see Sir Ray Lancaster's article Bacteria), are able to capture the nitrogen in the air which the rain brings down into the soil within reach of the rootlets (see the article on Botany). Leaving the exceptional cases aside, we see that plants depend on nitrogen compounds in the soil. Where do these come from? Electrical discharges in the atmosphere lead to the formation of nitric acid and nitrite of ammonia, which the rain brings into the soil. Various soil bacteria help to change nitrites into the more useful nitrates, on which the plants largely depend. But it must be admitted that other soil bacteria, which cannot be credited with philanthropy, work in the opposite direction. But when we pass from the extrinsic supplies of available nitrogen, such as thunderstorms and leguminous plants may afford, we face the fact that one cosmic generation lives on the graveyards of its predecessors. The bread we enjoy is a rehabilitation of the guano deposited by the birds of ancient sea cliffs. What we have just begun to do in illustrating the circulation of matter may be readily elaborated, and the idea may be extended to other elements. It should be kept in mind, however, that only a few elements share in the main circulation, for only about a dozen are always represented in living creatures, and a not much larger number makes up 99% of the earth's crust. But in an outline like this, the important thing is to make clear some of the germinal ideas of the science. And this is one, that many of the elements of the chemical world often change their partners in their unending dance. Catalysts. When we turn from a chemical treatise of a generation ago to one of to day, the whole atmosphere seems to be different, and one of the changes is suggested by the word catalysis, still unfamiliar to many. What does it mean? There exist certain substances, says Professor R. K. Duncan, which may lie in a vessel seemingly inert, and yet by their mere presence may dictate what action shall or shall not take place. A thing which has this commanding power is a catalyst, and the process is catalysis. The peculiar feature is that the substance which exerts a catalytic influence is not affected by what it does. It can be used over and over again. The presence of a very small quantity of platinum causes the combination of large quantities of oxygen and hydrogen, but it is not exhausted in the process. Professor Duncan gives a good example. Chromium chloride is a curious substance that exists in two forms, soluble and insoluble. The insoluble violet crystals may be left under water for days unaffected, but drop into the test tube a trace of chrominous chloride, even 25 millionths of a gram, and the violet crystals hasten to bury themselves in the water. The temperature rises, and an indigo blue liquid results. The mere presence of a trace of the catalyst has suddenly let loose the powerful affinities lying latent in the violet crystals, and the substance is dissolved. It is almost as curious as though a pound of salt thrown off the battery should dissolve Manhattan Island. This is an example of what is called physical catalysis. For the chemical properties of the chromic chloride are the same after as before, it is simply passed into solution. Ferments. To be included among catalytic substances, yet conveniently separated, are the ferments or enzymes produced by living creatures, for example, yeast plant and bacteria, or by living cells like those of the digestive glands. The fact that the yeast cell, the diameter of which is only 1/3000th part of an inch, is capable of so many chemical changes is one of the unexplained wonders of the world. As in the case of inorganic catalysts, so with these organic ferments, minute quantities can bring about chemical transformations of great magnitude, and at a very rapid rate. The number of ferments is legion, and they work like magic. Quickly and quietly they bring about changes which in the laboratory would require powerful reagents and high temperature. They are not living, but they are essential to life. They are always in a colloidal state, and they effect many different kinds of change, though each usually does only one thing. They help in building up and in breaking down. The changes they bring about take place most rapidly at a certain optimum temperature, and the ferments are susceptible to the influence of other substances, such as salts. Some always work in couples. As examples of organic ferments we may mention the ptyalin of the saliva, that changes starch to sugar; the pepsin of the stomach, that changes protein to peptone; the trypsin of the pancreas; and the diastase of the green leaf, that alters the solid starch into fluid transportable sugar. We know what these organic ferments are able to do, but we do not know what they are. Indeed, there are so many unsolved problems before the investigator of ferments, that the darkness seems almost greater than the light. Facts are rapidly increasing, but a rationale of the facts eludes us. 6. Crystals. We have spoken of crystals. Little is known of the determining cause of the formation of crystals, and the subject is too complicated a one to be dealt with in this work. The science of crystals is concerned with the study of the definite geometrical forms assumed by elements and compounds under certain conditions. The structure of a crystal consists of a small group of atoms which assume a regular arrangement in a fixed pattern. For instance, in a crystal of rock salt, which is built up of sodium and chlorine atoms, each sodium atom has 6 chlorine neighbours, and each chlorine atom 6 sodium neighbours, arranged in a manner typical of rock salt crystals. The atomic distance of these is about 100,000,000th part of an inch. Many chemical bodies assume the crystalline state when they change from liquid or gaseous condition into the solid form. They may be produced, for instance, by the evaporation of saturated solutions. It has been stated as a statistical truth that everything strives towards symmetry in so far as the environment will allow. Diamonds. A large number of definite chemical bodies are found in nature in crystalline conditions, such as the diamond. The diamond is the purest form of crystallised carbon. In the diamond every carbon atom is symmetrically surrounded by 4 other carbon atoms, arranged at the corners of a tetrahedron in such manner that the whole crystal is one continuous molecule, thus explaining, as it is thought, its great density and hardness. A crystal arouses our interest by reason of the regularity of its form, the perfection of its surfaces and angles, its transparency and brilliancy. A perfect crystal, like a diamond, is quite transparent and colourless, although it possesses that marvellous "fire" which we see oscillating with every movement. But most precious stones are tinged with grey, yellow, or brown. It is due to the high qualities of refraction and dispersion of light that diamonds give off the beautiful flashes of blue, gold, and red fire. Other colours, such as ruby red and emerald green, are more rare. The colour of many precious stones is really produced by minute proportions of impurity. The continued study of the formation of crystals, it is thought, may throw further light upon electrons and their connection with the structure of the atom. Colloids. Another set of facts of first rate importance relates to what is called the colloidal state of matter. In 1861 the Scottish chemist Thomas Graham noticed that some substances pass readily through a parchment paper, while others diffuse very slowly through. He called the latter colloids, from the Greek kolla, glue, and the former crystalloids. Weideveig and gum may illustrate colloids, sugar and salts crystalloids. But as many substances can exist as both, it is better to speak of the colloidal and the crystalloid conditions of matter. Moreover, the colloidal condition may be fluid, and then it is called a sol, or it may be gelatinous, even solid, and then it is called a gel. In any case, matter in the colloidal state is in the form of ultra microscopic particles of solid, or droplets of fluid, in suspension or in other manner of dispersion in another solid, liquid, or gas. The study of the properties of the colloidal state has proved of great importance in chemistry, and it is of fundamental interest to the physiologist, for living matter is in a colloidal state. Professor Bayliss writes: "Protoplasm in the living state has the properties of a liquid system, containing, however, particles of solids and droplets of immiscible liquids in a freely movable state. Many vital phenomena are bound up with the colloidal properties of the physical basis of life." We have said that many rare elements, though very important to us, lurk quietly in remote corners. Rare earths and their uses. Iron is common, but gold is comparatively rare. To get 2 ounces of the metal gallium, a great chemist has to work over nearly 600 pounds of crude material, but aluminum is easily procured. Why are half of the known elements so rare that few people know their names? As Professor R. K. Duncan writes: "Who, for example, has ever heard of, much less worked with, lanthanum, europium, erbium, neodymium, gadolinium, thulium, praseodymium, terbium, ytterbium, samarium, holmium, tantalum? Yet these forbidding names represent certain elements of matter, just as do others, such as sulphur, phosphorus, or lead, elements, too, unique in their properties and filled with all kinds of potential usefulness to man." We cannot answer this plain question: why are so many of the elements so rare? It may be that they are so rare because they are always changing into something else, or it may be that they are being made from other elements which are also rare. A significant fact is that the dozen rare elements mentioned above are found associated together as if they formed a family party. Let us pass to something easier: man's use of some of the rarities. Towards the end of the 19th century, Carl von Welsbach hit upon the brilliant idea of increasing the incandescence of a gas flame by making it heat up a cotton mantle impregnated with a rare element, such as lanthanum. Various improvements followed, but the principle remains the same to day. The cotton mantle was replaced by a fabric made of China grass, and the lanthanum was replaced by 99% thoria and 1% certuria, 2 rare earths which work into one another's hands in some rather mysterious way. The theory is obscure, the practical result is brilliant light. In 1897 Professor Nernst of Göttingen showed that a filament made of rare earths (thoria or zirconia) was at ordinary temperatures a non conductor of electricity, but a very good one when heated, even when lighted by a match. So we got the Nernst electric lamp, which gives a far finer light than the ordinary carbon filament electric lamp, but has the disadvantage of various complications and delicacies. Other rare elements have been tried, each with its own virtues. Thus there is a lamp with a filament of the very rare osmium, probably the most refractory and unalterable solid known to science, and therefore furnishing a filament with a very long life. There is another with a filament of the unrustable, steel hard element called tantalum, which occurs in South Dakota and in Australia as part of the mineral called columbite. Still more recent, and also very efficient, is the lamp with filaments of the rare metal tungsten. It must be noted that there are many effective lamps, such as the carbon lamp, which do not use rare earths, but it is of interest to realize that some of the rarities among the elements are common in the lamps of our houses and streets, and that academic curiosities have become of everyday practical utility. But man has not been able to devise a light as economical as that of the firefly. And yet we cannot pass from this subject without some appreciation of the progress that man has made in the art of producing light. It is a sort of index of his ascent. This was well expressed, for the time, by Sir William Crookes' preface to the first edition of Faraday's Chemical History of a Candle. From the primitive pine torch to the paraffin candle, how wide an interval! Between them how vast a contrast! The means adopted by man to illuminate his home at night stamps at once his position in the scale of civilization. The fluid bitumen of the Far East blazing in rude vessels of baked earth; the Etruscan lamp, exquisite in form, yet ill adapted to its office; the whale, seal, or bear fat filling the hut of the Eskimo or Lapp with odour rather than light; the huge wax candle on the glittering altar; the range of gas lamps in our streets, all have their stories to tell. All, if they could speak, and after their own manner they can, might warm our hearts in telling how they have ministered to man's comfort, love of home, toil, and devotion. This was well said, but we have had a glimpse of what might be added thereto: of incandescent mantles made of rare elements gathered, often laboriously, from the far corners of the earth; of delicate metal filaments whose toughness is such that the resistance they offer to the passage of electricity produces a most excellent brilliance; and of subtleties on the inventor's horizon which promise still more perfect light. A story about helium. The element helium was first detected in the sun by means of the spectroscope. It was 25 years later before it was recognized upon earth. How important and unlooked-for results may follow from scientific investigations and discoveries is illustrated in this case, as in many others. Helium is chemically inert. Like argon, it unites with no other chemical element. It is wholly indifferent to them all. This means that helium cannot be burned. In this connection a curious story is told. It is the next lightest gas to hydrogen, and unlike hydrogen it is non inflammable. In the late war the belligerents anxiously searched for a gas to fill airships which would be light and non inflammable. The great drawback to the German Zeppelins was that they were filled with a highly inflammable hydrogen. The Allies made a discovery, thanks to a wide awake enthusiast who suggested helium. But helium was enormously expensive to produce. However, there are in Texas certain gas wells which yield helium. Large plants were constructed with haste to recover helium from the natural gas by means of liquefaction, with successful results. Mr. C. G. Abbott tells the sequel. The matter was, however, kept a well guarded secret. Even the name was hidden. Photographs of the plant taken were labelled "Argon Manufactories." The idea was spread that the purpose of the experiments was to produce a new variety of poisonous gas for warfare, or perhaps a special variety of gasoline for use in airplanes. All sorts of camouflage were adopted to prevent the enemy from learning the true purpose of the experiments. So far had the work progressed that at the time the armistice was signed a consignment of 150,000 cubic feet of helium was on dock at New York, waiting to be sent to France to be used by the Allies for their balloons. Plans were on foot for increasing the output of helium enormously, so that it was probable that had the war lasted until the summer of 1919, the Allies could have employed helium gas for observation balloons and for Zeppelins with entire immunity from all possibility that they could be shot down with incendiary bullets. This may serve as a final diagrammatic instance of the endless ways, ever increasing in subtlety, in which the chemical world intersects with that of human life, both in its heights and in its depths. Chapter 22.
Of the Outline of Science, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Outline of Science by J. Arthur Thomson. Chapter 22. The Chemist as Creator. Modern chemistry practically dates from the time when the burning fire became intelligible, when the great French savant Lavoisier made it clear that a burning substance unites with oxygen from the air and gives off an acid, carbonic acid gas. He proved with his fine balance that the increase in the weight of the substance burned corresponded to the loss in weight in the surrounding air. This does not sound very exciting nowadays, but it was epoch-making, for Lavoisier realized that in all chemical operations it is only the kind of matter that is changed, the quantity remaining the same. The conservation of matter. This was the discovery of the conservation of matter, one of the foundation stones of chemistry, and not only a foundation stone, but a touchstone of accuracy, for it was henceforth certain that in every chemical operation the accounts must balance. The total mass of the substances taking part in any chemical operation remains constant, no matter what kaleidoscopic transformations may be effected. Since the masses of bodies are at any one place exactly proportional to their weights, the fundamental idea may read that in any series of chemical operations the weight at the end must equal the weight at the beginning. When Lavoisier made one of his famous experiments of passing water vapour over red-hot iron turnings, and collecting the hydrogen which was thus produced from the water, he weighed everything, the water to begin with, the iron turnings before and after, and the hydrogen gas as the issue, and his accounts balanced. Nowadays we are so sure that the accounts must balance that if they do not, then we must discredit the experiment. The solid ice becomes running water, which is caught up into the air as mist, which may become rain on the cold surface of the mountains. But in all the protean changes there is neither creation nor destruction. We can neither create nor destroy the smallest particle. The elements which enter into the composition of the soap bubble film are as lasting as those which form the granite rocks. Nothing can go lost. That is certain. At the entrance of a great exhibition there is usually a change office, which is the seat of busy operations throughout the day. Sometimes a visitor comes with a £1 note, which is not acceptable at the turnstile, and asks for small money. Sometimes a tramway conductor comes with 120 pennies and begs for something lighter, and there are all sorts of operations. But if the change office is fortunate enough to have perfectly accurate operators, it will not make anything or lose anything all the livelong day. The form of the money is continually changing, but the amount of money remains always the same. So it must be in all chemical operations. There cannot be anything massive or quantitative in the end which was not there in the beginning, nor anything in the beginning which has not its precise quantitative counterpart in the end. How then can we think of the chemist as creative? Constancy in the properties of elements. But we must go a step further. There is a remarkable stability in the properties of things. There are chemical elements in unthinkably distant stars, so the spectroscope tells us, which are the same as those on our own earth. Moreover, as the spectroscope continues to tell us, the properties of these elements remain the same, whether here or there. A molecule of hydrogen in the dog star Sirius seems to behave just like a molecule of hydrogen in a London laboratory. The furniture of the earth and the heavens may change from style to style, but the fundamental properties of its constituents remain. This conclusion requires careful handling, in view of the disintegration of the atom in radioactive substances. But on the whole, there remains validity in what Professor Clerk Maxwell said in his famous Discourse on Molecules in 1873. Though in the course of ages catastrophes have occurred and may yet occur in the heavens, though ancient systems may be dissolved and new systems evolved out of their ruins, the molecules, a modern chemist would say atoms, out of which these systems are built, the foundation stones of the material universe, remain unbroken and unworn. They continue this day as they were created, perfect in number and measure and weight. In the face of this, how can we speak of the chemist as creator? Making vital products artificially. The first reason for calling the chemist creative is to be found in the fact that he has been able to build up artificially what used to be regarded as exclusively vital productions. This is called chemical synthesis, and its development forms one of the most interesting chapters in the history of science. The beginning of the triumphant progress was in 1828, when Wohler discovered that the salt known as ammonium cyanate changes spontaneously, when its solution is evaporated, into urea. Why should that be important? The reason was this. Urea is a nitrogenous waste product formed by mammals and filtered out of the body in the urine. Like other products of the living body, urea was regarded as a characteristic vital product. But cyanate of ammonia can be made apart from living creatures, and yet it readily changes into urea. This was the thin end of the wedge. The substances made by living creatures could no longer be kept on a platform by themselves. Wohler's experiment showed that one of them at least could arise apart from life altogether, and just about the same time, 1826 to 1828, another pioneer, Henry Hennell, was able to build up alcohol from a simpler carbon compound, ethylene. What was regarded as the yeast plant's exclusive prerogative was attained along a different path, without any living organism at all. It is true that neither of these important steps received due attention. Wohler and Hennell were before their time, but they head the illustrious list of synthetic chemists. Outdoing nature. Indigo, much used in dyeing and formerly obtained from the indigo plant, is now made artificially, and the same is true of Turkey red dye, which used to be obtained from the roots of the madder. Vanillin, much used in confectionery, was formerly obtained altogether from the vanilla plant, but it is now made in large quantities artificially. Oil of wintergreen, used in medicine, was formerly obtained from the plant pyrola, which grows in shady woods, but is now made artificially. The sepia which painters use to employ for sombre pictures was obtained from the ink bag of sepia and other cuttlefishes, a bag of waste products which these big-brained creatures eject into the water to cloak their retreat from their enemies. But if a modern painter uses sepia, it is an artificially built-up pigment. It does not come from the cuttlefish. So we might continue through a long list. There has been an artificial synthesis of sugar, of caffeine, of salicylic acid, and scores of other complex substances. The list grows every year. The chemist outdoes nature. There are 2 points of great interest here. The first theoretical, the second practical. The interesting theoretical point is that the artificial production of a certain organic compound does not usually correspond to the natural production of the same substance. Thus the artificial production may require great heat, which is out of the question in a plant or animal. We take a walk in a wood in spring and pull a few of the clover-like leaves of the wood sorrel, whose technical name is worth recording, Oxalis acetosella. We taste these beautiful leaves, almost as beautiful as the pendant, translucent white flower bells. We enjoy the pleasant oxalate taste, like the acid drops of our childhood, due to the salts formed in the course of the chemical routine of the wood sorrel's life. How these pleasant oxalate salts arose in the wood sorrel's leaves is not our question just now, except to this extent, that they certainly were not formed in the same way as the synthetic chemist, the magician of his craft, builds up oxalates in his laboratory. The second point is strictly practical. If living plants make indigo and living animals make sepia, why should man be so proud of an artificial imitation, which means an ousting of natural production? The answer is not always easy, but it is clear in cases where the chemist can manufacture large quantities of a valuable material without great expense. Thus he has been able to build up the potent substance called adrenaline, used in stopping bleeding and for other purposes, a substance which is produced only in very small quantities by the suprarenal capsules of animals. It is one of the important internal secretions or hormones which are discussed elsewhere. To obtain adequate supplies of adrenaline for medical purposes would mean killing a large number of animals. How much more economical when the synthetic chemist can build up this precious substance from simple constituents. In so doing, he is a creator. Coal tar colors. The chemists have not been content to imitate nature. They have gone one better. They have made new things, and fine illustrations of this may be found in the story of coal tar products. Everyone knows that when coal is used to make gas, there is a residue of useful coke and of coal tar. This strong-smelling, dark-colored coal tar used to be regarded as a troublesome byproduct. It is now known to be a sort of treasure house of dyes and drugs, of perfumes and explosives. It has been called one of the most useful substances in the world. The reasonable question at once arises, why should coal tar be such a treasury, a magic purse of Fortunatus, as Dr. Slosson says? The answer is twofold. A, that coal tar is a mixture of organic substances which were built up in the ancient club moss and horsetail forests, the remains of which formed the coal deposits. And B, because the chemist can juggle with the primary products so as to build up quite new artificial ones. When the coal tar obtained from the distillation of coal is redistilled, it yields materials like carbolic acid, phenol, so much used as a disinfectant, like naphthalene, used in driving moths away from furs, like benzene or benzol, and so on. The residue left after about 10 colorless liquids or white solids have been separated off is the familiar black pitch. 1. The chemist's unit is a molecule, the smallest amount of an element that can exist separately, and he is accustomed to picture the molecule as composed of atoms linked together by hands or bonds. Thus the molecule of hydrogen, H, may be pictured as H-H, each atom having one hand. The atom of carbon is pictured as if it had 4 hands, and thus the symbol of the simplest hydrocarbon, marsh gas, is carbon attached to 4 hydrogens, or CH4. Now the coal tar product called benzene, B-E-N-Z-E-N-E, note the previously mentioned benzene, B-E-N-Z-I-N-E, is a different thing altogether, has the puzzling formula C6H6, puzzling because it is not easy to see how the 4-handed atoms of carbon can be satisfied with 6 one-handed atoms of hydrogen. The puzzle was solved by the German chemist Kekulé, who saw that the symbol of the benzene molecule should be like a ring or hexagon, in which the carbon atoms are linked together by alternating single and double bonds, while the hydrogen atoms hold on to the outside hands. To explain the importance of this, we quote a paragraph from Dr. Edwin E. Slosson's Creative Chemistry, 1921, a brilliantly successful popular exposition of chemical synthesis. We need not suppose that the benzene molecule, if we could see it, would look anything like this diagram of it, but the theory works, and that is all the scientist asks of any theory. By its use, thousands of new compounds have been constructed which have proved of inestimable value to man. The modern chemist is not a discoverer, he is an inventor. He sits down at his desk and draws a Kekulé ring, or rather hexagon. Then he rubs out a hydrogen and hooks a nitro group, NO2, onto the carbon in place of it. Next he rubs out the O2 of the nitro group and puts in H2. Then he hitches on such other elements, or carbon chains and rings, as he likes. He works like an architect designing a house, and when he gets a picture of the proposed compound to suit him, he goes into the laboratory to make it. Perhaps what he makes may bear the hyphenated name sodium ditalo-disazobeta-naphthylamine 6-sulfonic beta-naphthylamine 3,6-disulfonate, the commercial contraction of which is brilliant Congo dye. To sum up, the coal tar yields 10 primary products or crudes, like benzene. These have yielded some 300 intermediates, like aniline, and from these have been created literally thousands of dyes of all hues and shades. The history is very interesting, and it is briefly this. After some pioneer discoveries, a big step was taken by Hofmann, a student in Liebig's laboratory, who showed that brilliant colors could be obtained from certain coal tar products chemically related to an aniline oil, which had been obtained long ago by Zinnin from natural indigo. Hofmann went to teach in the Royal College of Science in London, and he had as one of his students a boy of 15, William Henry Perkin. This genius was set to work to prepare artificial quinine, and in 1856 he discovered mauve, the first of the aniline dyes, and a new substance in the world. 10 years later he discovered how to produce artificially the coloring matter called turkey red or alizarin, which had previously been obtained from the root of the madder plant. At one time 500,000 tons of madder were raised annually in France, but after Perkin's discovery, as Professor Slosson puts it, the madder fields of France were put to other uses, and even the French soldiers became dependent on made-in-Germany dyes for their red trousers. The British soldiers were placed in a similar situation as regards their red coats, when after 1878 the Azo scarlets put the cochineal bug out of business. For it was from the body of the female cochineal insect, Coccus cacti, a native of Mexico to start with, that the scarlet coloring matter was obtained. We must not linger over the story of the coal tar colors. There are so many other creations to be discussed. What happened in regard to turkey red happened in regard to indigo, which came originally from an Indian plant related to the British woad; in regard to Tyrian purple, which came originally from a Mediterranean sea snail, Murex, and in so many other cases. It is a matter for regret that when Hofmann returned to Germany he practically took the young industry with him, an instance of British lack of imagination and foresight. By 1914 the Germans were manufacturing more than 3/4 of all the coal tar products of the world, and supplying material for most of the rest. It must be understood that the coal tar dyes are often good for much more than dyeing the robes of cardinals, the uniforms of soldiers, the socialites' necktie, and even ladies' ribbons. Thus, to mention only one, the dye called flavine is a quick killer of the microbes of abscesses. An ally to the coal tar dyes are many coal tar drugs, many of them not unmixed blessings, like aspirin, phenacetin, sulfonal, and veronal. Artificial perfumes. Nothing derogatory is implied in the term artificial, for why should indigo built up by the devices of the rational chemist be necessarily inferior to that elaborated in the indigo plant, or why should the musk made from a coal tar product be necessarily inferior to that secreted by the musk deer? That the artificially produced substance is not made in the same way as the naturally produced substance is certain, but chemically they are the same when they are finished. It is possible that minute impurities or accessories cling about the natural product, which give it a charm of individuality, like that distinguishing a woodcut from a zinc block, or a wrought iron gate from one of cast iron. In any case, the main fact in regard to perfumes, as in regard to more important products, is that man first sought laboriously for the natural. He then tried to adapt nature to his purposes, for example, by growing acres of scented flowers, and third, he has gone on another tack altogether, that of creating for himself. Thus the chief ingredient of attar or oil of roses is geraniol, which can be made synthetically, and the fragrance of orange flowers has been successfully captured by the artificial building up of neroli. What is true of perfumes holds also for flavors, appealing to the other chemical sense, taste, the twin sister of smell. Thus vanillin, artificially synthesized in 1874, is extensively used instead of the identical vanillin from vanilla beans. Our only protest is this: let the natural and the artificial products compete fairly. Let the aesthetes decide how far they are physiologically and psychologically equivalent. Let us pay accordingly, if we please. But do not mix synthetic geraniol with attar of roses. Synthetic rubber. India rubber or caoutchouc is a gum which occurs in the milky juice of many plants, and abundantly in a few, especially in certain trees of the spurge and the fig orders. The milk flows out when the tree is cut, and rubber trees are now cultivated in many places where they are not native. The material is used, as everyone knows, for tires, waterproofs, galoshes, hot water bottles, syringes, stoppers, and in hardened form as vulcanite. It has almost been forgotten that the name rubber referred to its early use as an eraser. Another gum, known as gutta percha, is used for isolating submarine cables and for making golf balls. When rubber is heated in a retort, it splits up into a benzene, benzine, like liquid called isoprene, and the synthetic chemist's problem was first to make this isoprene artificially, and second, to change it into caoutchouc. The whole story is an extraordinary one, but we can only say that isoprene can be made artificially in various ways, for example, from the fusel oil yielded by fermenting potato starch, and that isoprene can be changed into caoutchouc in various ways, for example, by drying it over metallic sodium. In 1912 there were exhibited in New York 2 automobile tires of artificial rubber which had run 1,000 miles. But while the problem has been solved scientifically, it has not been solved industrially, for it does not pay to get isoprene from potatoes or from turpentine. The most promising method is perhaps to heat coal and lime in an electric furnace. They unite to form calcium carbide, which in contact with water yields acetylene, and from this gas it is possible to make isoprene and therefore rubber. Yet it remains more profitable to go to the rubber tree. Sugar making. For many ages men knew of sweetness only from fruits and honey, but in the course of time they learned to press the sugar cane. How this sweet reed was carried from the Far East to the West Indies is an interesting story, but it does not concern us here, nor how Napoleon was instrumental in rivaling the sugar cane with the beetroot, which is rich in precisely the same sucrose. Of formula carbon 12, hydrogen 22, oxygen 11. Of course, all green plants make sugar, but only the cane and the beet, we need hardly count the maple, do so in sufficient abundance to be worth tapping, except through bees or as concerns their fruit. What the chemist has done in regard to sugar is to distinguish its different natural kinds, to make some new ones on his own, and to make it possible to get this valuable nutrient very pure. As Dr. Slosson says, common sugar is almost an ideal food, cheap, clean, white, portable, imperishable, unadulterated, pleasant-tasting, germ-free, highly nutritious, completely soluble, altogether digestible, easily assimilable, requires no cooking, and leaves no residue. Its only fault is its perfection. It is so pure that a man cannot live on it. In fact, to make it more than a fraction of the diet is dangerous, and some people with a slight twist in their chemical routine, metabolism, should not take it at all. And here is a point where the creative chemist came in. For an American investigator, Ira Remsen, afterwards president of Johns Hopkins University, accidentally discovered a coal tar derivative which he called saccharin, several hundred times sweeter than sugar, yet not a sugar at all. It has no nutrient value, but it flavors tea and coffee, and it is not injurious to those who cannot take sugar. 2. Chemical conjuring. We never tire of watching a conjurer who turns a crumpled handkerchief into a white rabbit, and that into a pigeon, but there is much more real conjuring in the chemical laboratory. The chemist is a transformist. With a wave of his wand he changes soft unsaturated fats, which are apt to become rancid and smelly, into hard saturated fats which last and keep sweet. With another wave he transforms rank fish oil so that it can be used for soap or even for food. From beef fat the chemist originally made margarine, but other sources of fat, from coconut and cottonseed, from peanut and soya bean, may now be added to this excellent composite butter. The fact is, the animal fats are being more and more displaced by vegetable fats. But our point was simply that with a little coaxing, the chemist can change a material so that we do not know it when we see it, and that he can make excellent butter without applying to the cow. Transformations of cellulose. The cell walls of plants are made of cellulose, a carbohydrate with the same formula as starch, carbon 6, hydrogen 10, oxygen 5, which often hardens into wood. We necessarily eat cellulose when we eat cabbage and the like, but we do not get much good out of it, and it is more important in other connections. It has gone to make coal, it forms wood, and it is the convenient starting point for many of the chemist's transformations. For although he may go back to inorganic elements, carbon, hydrogen, oxygen, and nitrogen, it is much more convenient not to have to begin at the very beginning. From wood pulp most modern paper is made, and the delicate fibers seen in paper when examined under a microscope are the remains of the cell walls of the plants. Cellulose is also used for paper cups and napkins, twine and suitcases, but it is even more important when used along with other materials as in mercerized cotton and the artificial silk this can be made to yield. In this connection Dr. Slosson makes good use of the story of Nobel's cut finger. Alfred Nobel was a Swedish chemist and a pacifist. One day while working in the laboratory he cut his finger, as chemists are apt to do, and again as chemists are apt to do, he dissolved some gun cotton, cellulose treated with nitric acid in the presence of sulfuric, in ether alcohol and swabbed it on the wound. At this point, however, his conduct diverges from the ordinary, for instead of standing idle and impatiently waving his hand in the air to dry the film as most people, including chemists, are apt to do, he put his mind on it, and it occurred to him that this sticky stuff, slowly hardening into an elastic mass, might be just the thing he was hunting as an absorbent and solidifier of nitroglycerin, the liquid result of mixing glycerin with nitric and sulfuric acids. So, instead of throwing away the extra collodion he had made, he mixed it with nitroglycerin and found that it set to a jelly. The first of the high explosives of modern warfare. Everyone knows that this collodion is much used as new skin, which has saved many lives, and in the cameras and cinemas that have made so many people happy. And one might go on to show how the cellulose of the sawdust heap can be used to make the soles of boots, the cushions of the car, the celluloid of the toilet table, and much more besides. 3. Capturing nitrogen. All living matter consists in part of proteins, nitrogenous carbon compounds such as white of egg, casein, gluten. It follows that a normal diet, to keep this living matter a-going, must include a supply of nitrogen. Animals cannot utilize nitrogen except in the complex form of proteins, which have been worked up by other animals or by plants. Plants get their nitrogen supplies from nitrates, like saltpeter, and similar nitrogenous salts in the soil. Therefore, it becomes of fundamental importance that the supply of nitrogenous salts in the soil should be kept up. To some extent this comes about very naturally when the withered residue of plants is, with the help of earthworms, incorporated again in the soil, or when a dead animal is buried by sexton beetles and decomposes. The same result is reached when what remains of a crop is ploughed in, or when the stable manure is spread upon the fields, and eventually takes the form of ammoniates or the like, which the plants can utilize. On the other hand, when forests or coal seams are burned by man, fixed nitrogen is lost in the combustion, and the amount of free nitrogen in the atmosphere, 4/5 of the whole, is increased. Combined nitrogen is similarly lost when gunpowder explodes, and a small cannon shot, using up only a pound of gunpowder, destroys combined nitrogen to the extent of the free nitrogen in 3 million liters of atmospheric air. In this sense, Professor Bunge writes, it may be affirmed that every shot from the firearm kills, that it destroys life whether the ball strikes a living being or not. For no life is lost by the death of the individual. From the decay of the body equivalent new life arises. But the destruction of combined nitrogen means the definite diminution of the capital, upon the amount of which the total number of living beings depends. Obviously, this is taking a very quantitative view of life. The vital equivalent of a lost leader is not calculable. We see, then, that one of the farmer's main problems is to keep up the supply of combined or fixed nitrogen in the soil. A cheap way of doing this, referred to in the chapter on botany, is to cultivate leguminous crops with root tubercles, for by means of the partner bacteria in the root swellings, such plants are able, in a way not yet understood, to capture the free nitrogen of the air and fix it. If these crops are plowed into the soil, in whole or in part, they will make it rich for other and more valuable growths. But this is a slow process, and what the farmer does is to manure his fields, with, in particular, a supply of nitrate brought from the saltpeter fields of Chile. But Chilean nitrates are expensive, and the supply is limited. Therefore we see the enormous importance of the chemist's discovery that nitrates can be made at home. There are some Swiss valleys nowadays which are glacier at one end and 98% nitric acid at the other. The chemist has discovered how to make fertilizers, and therefore bread, out of the thin air. It has been known for a long time that a flash of lightning passing through the air may separate nitrogen atoms from one another and oxygen atoms from one another, with the results that some of the isolated nitrogen atoms unite with some of the oxygen atoms and yield nitric oxide, the first step to something better. What the chemist did was to substitute for the lightning a gigantic electric arc through which the air is run rapidly, lest the terrific temperature, for example 6,300 degrees Fahrenheit, undo what has been done. When the energy for producing the electric arc can be obtained from a handy waterfall, whether natural or artificial, the relative cheapness of tapping the store of free nitrogen in the air is evident. In Germany, where water power is not so available as in Scandinavia, they hit upon another way of capturing the nitrogen of the air, the well-known Haber process. The elements used in this case are nitrogen and hydrogen. The result is ammonia, and the agent is not an electric furnace, but a quietly working rare metal, such as uranium, osmium, or platinum, which acts in a mysterious way as a catalyst, bringing elements that become intimate with it into union with one another. It is not to be supposed that the Haber process is a simple affair, for great pains have to be taken to get the nitrogen and the hydrogen in a very pure state before they are submitted to the catalytic action of the rare metal. Moreover, when the ammonia has been produced, it has to be changed into the more useful form of nitric acid, which involves another appeal to a catalyst, a platinum gauze, in the Ostwald process. The extent to which the air is today worked for raw materials is very wonderful, such, for example, as oxygen, which is used extensively in engineering industries with acetylene to make intensely hot flame for welding and other processes. Nitrogen, as we have seen, is obtained from the air on a great scale for the manufacture of fertilizers, the output of which is enormous. Argon and neon also are trapped from the air and are used in incandescent electric lamps. We cannot leave the subject of fertilizers without saying a little about cyanamide. When a strong electric current is passed through a mixture of lime and coke, the metal calcium joins to part of the carbon, yielding calcium carbide, composed of 1 calcium and 2 carbons, CaC2, the stuff which, along with water, produces acetylene gas. Now, if a stream of nitrogen be passed over hot calcium carbide, it is captured and forms calcium cyanamide, CaCN2, a stony material sold as a fertilizer, lime nitrogen. But if the calcium cyanamide be treated with superheated steam, it yields ammonia, and from ammonia can be produced nitric acid, and from that, fertilizers, which mean more bread. It is useless to pretend, however, that this is more than one side of the story, for whether it be primitive gunpowder made by grinding up saltpeter, charcoal, and sulfur into a black powder, or nitroglycerin or gun-cotton, or these two combined, or TNT, all the explosives of war depend upon the readiness of the nitro group, NO2, to break up. For nitrogen does not readily combine with other elements, and when it does so it is very prone to break off the connection on even slight provocation. The potash supply. A typical plant food is saltpeter or potassium nitrate. The nitrate part can now be snatched from the air instead of being dug from the guano beds of Chile. But what of the potash part? A ton of wheat, Dr. Slauson says, takes away from the soil about 47 pounds of nitrogen, 18 pounds of phosphoric acid, and 12 pounds of potash. If the farmer is to go on, he must replace not only the nitrogen, but the phosphorus and the potash. The world consumption of potash for agricultural purposes is enormous. Now, the great natural source of potash is at Stassfurt in Germany, a vast bed where the evaporation of seawater floods left in bygone millennia crystalline deposits of the salts which had been dissolved out of ancient rocks and left them well arranged. In 1913, the United States imported 1 million tons of Stassfurt salts, for which the farmers paid over $20 million. Obviously, the potash supply has had to be looked for somewhere else, and the chemist has to lead the search. There are abundant salts of potassium in the rocks, for example the feldspar of granite, but the difficulty is to get the potash out or to get it out cheaply enough. As Dr. Slauson says in his inimitable way, a farmer with his potash locked up in silicates is like the merchant who has left the key of his safe at home in his other trousers. He may be solvent, but he cannot meet a slight draught. It is only solvent potash that passes current. Use is now made of the potash in wood ashes, the potash in the waste liquor of beet molasses, the potash in seaweeds, and so on, but the potash problem remains unsolved outside Germany. Wealth out of waste. In many cases, as we have seen, the chemist made a new thing, such as chloroform. In many cases he made an old natural product in a new artificial way, as in the case of indigo. But in other cases his ingenuity has taken the form of discovering a use for what was previously regarded as worthless. Let us take a few examples. For many a year no one thought of utilizing the cotton seed that used to be thrown away or burned when the precious fiber was collected. Nowadays it is used in 100 ways, yielding cotton meal for cattle and oil for table use, writing paper and putty, fertilizers and soap, varnishes and smokeless powder. Even from such an apparently trivial source as the seeds of the tomato fruit, formerly discarded in the canning factory, there can be extracted over 20% of an edible oil. The chemist has led the world to a new economy. Summary. The story of the chemist's achievements as a creator is one of the most brilliant chapters in the history of science, and not without its romance. We strongly recommend Dr. Edwin Slauson's Creative Chemistry from 1921, a book that reads like a novel, to which we have been greatly indebted in writing this short article. We have not been able to give more than samples of what has been accomplished. What was procurable in small quantities and at great expense as a natural product can now be made artificially and cheaply. What was once procurable but has become unavailable by reason of exhaustion or political changes can be made from simple materials and independently of any particular locality. Hundreds of entirely new things, which the world never saw before, have been synthesized. Vast quantities of material, previously unused or thrown away as waste, have been utilized as the foundation of new wealth. So the story runs, and there is no telling what chapters are to follow. It is by no means fantastic to suggest that some new biochemical discovery may alter the whole bread-and-butter problem of mankind. For a long time the chemical investigator was concerned with analysis, but to this he has added synthesis, and in so doing he has already made the world new, both for evil and for good. End of chapter 22. End of section 14.